Okay, great. Thank you for that introduction. So my name is Min Roh, and I'm a postdoc in the Scalar Solvers group. So this talk, I'm excited to talk about doing the nuclear strength function calculations using ideas from numerical dynamics. Okay, so to start off, what is a strength function? So a strength function is a measure of how the nucleus in an atom responds to a external probe, such as this light or neutrino. So one instance, for example, is how the nucleus goes through a beta decay, where the neutron transition to protons or vice versa. So here's a simple analogy of what a strength function is. So think of a nucleus as a bell. You tap the nucleus with something like light or a element, and you can change how you tap the bell. So you can tap it harder or using different notes, and how the bell rings, how loudly it rings, basically responds to what the strength function is. So if you look at this graph of a strength function that in the middle, where the nucleus likes to respond to the rotation of these peaks, and how strongly the nucleus responds to the height of the peaks. So going back to the example of beta decay, where the neutrons could transition to protons or vice versa. So if you look at the frequency region where we have the high peaks, that's where that transition is most likely to occur. So why do we care about all these? Well, nuclear physicists and astrophysicists, they care about this strength function because it can help them predict how and what elements are made from all these collisions and so on of the nuclei of the stars, as well as how the neutrinos get absorbed or scattered in things like supernovas or stars. So a prototypical of solving for computing the strength function is by looking at what are called the linear response equation, and which are solved using iterative methods known as the finite amplitude method or the generalized minimal residual method. However, these are kind of costly in practice because you need to solve one frequency at a time. And why is this an issue? Because oftentimes we are interested in the entire shape profile of the strength function for the entire permissible frequency range. But since these are targeting one frequency at a time, if we're interested in a finer resolution of the strength function, as well as the greater range of the strength function graph, we need many more runs of these two methods that rely on using the linear response equation. So in our approach, our goal is to, instead of solving many different frequencies by doing many different ones, we do it in one shot, in one run. And the key idea behind of doing this is turning the linear response equation that I mentioned into an eigenvalue problem. It's the same reformulation. It's the same equivalent reformulation. So what this allows us is to solve the eigenvalue problem once instead of solving the linear systems that we see in the linear response equation many times for different many frequencies. So how exactly are these eigenvalue problem related with the strength function? So that is like what kind of information do we get from the eigenvalue problem? Well, it turns out that the position of the peaks correspond to the eigenvalues, the omega and negative omega, the coming pairs. So this is where the nucleus responds, as well as the eigenvectors, the u's and v's. They tell us how strongly the nucleus responds, which is the height of the strength function. So we can actually further reduce this problem, this eigenvalue problem, into half. We have this matrix, the corresponding matrix AB minus B minus A, and that's something that's known as the Casita matrix. And we can reduce that into a half-size problem involving the matrix MK, where M is A plus B, K is A minus B. And this reduced eigenvalue problem, the eigenvalues are omega squared, so we can just simply take the square root of that. As well as the eigenvectors are U minus V. So, and by making use of this kind of a nice relation that we have, where U plus V is equal to the K G minus V omega to the -1, we can easily get the eigenvectors, the U's and V's for our interest. So although we've reduced the size of into half into this MK matrix, in practice, this is still quite large. It can be of size hundreds of thousands. So the way we want to, so the full diagonalization, computing the full complete eigenvalue problem like that is still very costly, still very expensive. So the way we approach this is using the classical method known as the Lanczos method, which is a data method. Basically, the core idea is you reduce this large size MK into a tridiagonal matrix, M, where this M stands for how many iterations of Lanczos you've done. So, and Lanczos method, as you may well know, it's usually done for the symmetric matrix problem, which is not the case for the MK matrix that we're working with, but it's self-adjoint K product. So at the end of the day, we get the symmetric tridiagonal symmetric TM matrix. Okay, so here are the numerical results that we looked at. This is we looked at doing the beta decay of a small nucleus where we have, the system is small enough that we can compute the true strength function, and this is possible by doing the full diagonalization of matrix. And that's represented by the red dashed line here. And we see that with just 50 Lanczos iterations, we get a pretty good approximation of what the true strength function looks like. It's able to capture that largest peak that we see in this frequency range. And by the time we get to 150 iterations, even in that complex area of where you have a lot of these small peaks, it's able to fully capture that quite accurately. So compared with the existing method, so here we looked at the GMREDs. The key point is that the Lanczos method can achieve comparable accuracy while doing so at a lower cost. So on the left, you see an absolute error relative to the true strength function. So you see the bunch of dots, black dots that you see, those are the GMREDs. Remember, you have to do each GMREDs iterations for each of these dots. And Lanczos is able to match that accuracy while also making really good approximations for the entire spectrum, as you can see. And this is all doing so while being faster. Not only is it more accurate, it's making the entire spectrum approximation at a faster time for the two nuclei that we looked at, lithium-6 and neon-22. So in summary, the key takeaway on this talk is that nuclear strength are important in nuclear physics and astrophysics. There are existing methods, but they can be expensive because you have to do many runs for different frequencies. And our approach was to do it in a single run or to capture the entire range of frequencies. And this is possible by reformulating into eigenvalue problem. And we further reduced that problem into half with Lanczos method. And this approach was as accurate as the existing method GMREDs, and it took less time.